Peltier based cooling. How do we do it? Let us have a look at this visualization. We have seen this before. This is the cold junction, this is the hot junction. In between you have a heat pump, which is the Peltier element, which is taking in the electrical energy and extracting QC amount of heat from the cold junction and passing it on to the hot junction. Let us replace this heat pump with a square box resembling the Peltier element, having two terminals, electrical terminals, as shown like this. Now to the electrical terminals we connect the output of a DC-DC converter. So this is the output of the DC-DC converter. Power is flowing like this. On the input of the DC-DC converter, we have this buffer capacitance, and the terminals of that is connected to a PV source, PV module, PV array, PV panel. All these are PV sources, appropriately sized such that it is connected to this terminal. There is power flow from the PV module into the DC-DC converter, and from the DC-DC converter output into the Peltier. So this is VT, terminal voltage of the PV module. You have the duty cycle, which will be used as the control input, and you have VP, the terminal voltage of the Peltier element. There is also another important parameter, IP, which is the current that is being fed into the Peltier element to achieve the pumping action, the heat pumping action. So we know the we know the resistance, electrical resistance in ohms that is offered by the Peltier element, which is given in the data sheet we saw, and then using that you can adjust the duty cycle accordingly. Along with the insulation, the duty cycle can be controlled such that the PV module is operated at the maximum power point. This we know how to do. So a maximum power point operated PV panel DC-DC controller setup can be used to power the Peltier element. So the duty cycle can be used to control IP, the current that is fed to the Peltier junction, and control the amount of QC that can be extracted from the cold junction and then fed into the hot junction. So this is the process of heat pumping. But there is one major problem. Let us say that is the hot junction, and then I have a cold junction, and in between I am having this heat pump. QC is extracted from the cold junction and given to the hot junction as QH, which includes even the energy that is required for pumping. Now this hot junction is at a higher temperature than the cold junction, which is at a lower temperature. When heat has to flow from a cold, low temperature to high temperature, you need a pump. It is much more difficult. But from high temperature to cold temperature, the heat flow is automatic. You don't need you don't need the means of a pump. So automatically heat will find a path like this or like this, and then reach the cold junction, and the delta T, what you are trying to achieve, will actually come down, and the temperature difference between these two junctions will not be that much. So it becomes very, very important that not only do you have to pump the heat up, you should retain that heat there or remove it elsewhere so that it doesn't come back to the cold junction and reduce the delta T. It is analogous to a water pumping. Let us say water is pumped from a low level to a higher level, and if there is a large leak in the overhead tank, whatever you pump comes down, it never fills, and then all the water is still remaining in the bottom. The water pumping is not doing much work. Same way here also, if the heat is again coming back, the heat pump is not of much use. Therefore, it is important that you retain the heat on the hot side or remove it from the hot side to elsewhere, so that it doesn't come back into the cold junction. So the whole of the design of the Peltier based application should take this into account. And one of the most important thing is the heat removal and the thermal aspects. These are very, very important, and then we will have some look into this to see that how we go about designing Peltier based cooling applications. Let us discuss some examples and applications of Peltier based cooling. Consider a PCB. This green strip that you see here, consider that it is a PCB, and on top of that let us have a component which is becoming hot, which is dissipating power. So let me draw a component mounted on the PCB which dissipates power, and it is our objective to remove the heat from it and then keep it within a rated temperature, junction temperature, such that it operates properly. Now this component, at the center of the component, within its core in the junction, it is generating heat because of electric current going through it. There is power that is getting dissipated, and that power has to go out, and this point here can be considered as a heat source or heat that is getting generated, and it has to flow out from there in this fashion. So this is the heat flow, and then we'll call it as QC. So QC amount of heat is being extracted, that much amount of power is flowing out because of dissipation within this component, and it is becoming hot. Now let us see how we will build some relationship to design Peltier based cooling. Now let me call this central core where the heat is being generated as the junction. Most of the semiconductor junctions are the central core where the heat is getting generated in many of the components. So I will call that as J, and the heat is flowing out into the external ambient here, and I will call that one as the ambient, and I will put a dot there to represent the ambient, and I will call that one as A for ambient. So this here is a pictorial visualization of what is happening. Let us map this into a thermal visualization. So let me visualize it in a thermal fashion with the equivalent circuit. Now I will put a current source. The current source is representing the heat flow. The heat that is generated and that is flowing out is extracted out of this component. So this current source is flowing in this fashion. This node, I will call that one as J, and that is the junction representing this core here, which is then followed up by resistance. It is not resistance from the electrical circuit point of view, it is a thermal resistance. And on the other side, I have the completion of the circuit so that the power flows in this fashion. Just like an electric circuit, but it's not an electric circuit, it's a thermal visualization. Now this node, I will call it as ambient. And coming back to this physical picture visualization, this junction here is generating QC amount of power which is flowing out, as shown, and it is equivalent to having a current source here which is having a value QC, and that QC current source is flowing in this direction, and there is a drop across this thermal resistance, and that is the temperature difference between this and this. So now let us say that this QC watt is flowing. This node is at a temperature called Tj, that is the junction temperature, and this node is at a temperature Ta, and that is the ambient temperature. And this element I am calling it as R theta Ja, thermal resistance from junction to ambient Ja. So now let us try to see what is the relationship between all these parameters. So Tj minus Ta, I am interested in that. What is the delta T? Tj to Ta, what is the delta T? That is what is the potential to cause the heat to flow, and that is equal to this QC and thermal resistance. So I will call the R theta Ja thermal resistance into QC. In more generic form, I can say delta T is equal to thermal resistance into heat flow. If you want to write thermal resistance in terms of delta T and QC, we can write it as thermal resistance is delta T, temperature difference between 2 points, temperature difference across the thermal resistance, divided by QC, the heat flow through the thermal resistance. This is an important relationship which will be used in most of thermal visualizations. Remember this. Delta T is in degree Kelvin, QC is in watts. So thermal resistance is in a degree Kelvin per watts, or degree centigrade per watt, because when you take thermal delta T, it is a thermal temperature difference. So you could as well use degree centigrade per watt. Both are numerically okay. This component mounted on the PCB is dissipating an amount of power QC, and that is being given out to the ambient. And we saw that the equation is given by this relationship. This is Tj, the junction temperature, Ta, the ambient temperature, difference in junction and the ambient temperature, delta T, is equal to R theta Ja, junction to ambient thermal resistance, into the amount of power that is flowing, that is the heat flow, QC in watts. Now let me rearrange. Junction temperature is equal to T ambient plus R theta Ja into QC. Now here we know, let us say for example, T ambient can be found out. Let us say we will set it at maximum 40 degrees centigrade. R theta Ja, depending upon the component from the data sheet, we can get R theta junction to ambient, which will be, let us say for example, 10 degrees centigrade per watt. QC, the amount of power dissipated within the component, is 20 watts. So we need to remove 20 watts of power out of this component. Now using these numbers as an example, Tj, the junction temperature, works out to be 40 plus 10 into 20, so 240 degree centigrade. Now this is a tremendously high temperature, and most of the time the component would have blown by the time it crosses 150 degrees centigrade. So we should not allow the junction temperature to rise to that temperature, which means we should see that the heat is removed out of this component much more quickly. So how do we do that? You have no control in QC because that is dependent on other parameters of the circuit. You have no control on Ta because ambient temperature is not controlled by you, it is decided by the external ambience. The only thing that you can control is the thermal resistance. So this is what you can do something about, and you can reduce this. how do you reduce this? So that is where Peltier cooling comes into picture. So we will initially put a heat sink and see how the heat sink will reduce the junction temperature, and later we will put a Peltier element to cool this component, and then see how it will improve the heat removal out of the component. Let us zoom in here, let us magnify this and then look at the thermal resistance here. So we have the component placed on the PCB which is magnified, zoomed in, and we have the core where the heat is dissipated, and from that core we have a thermal resistance up to the case, and that is R theta junction to case. So I will say junction to case. Then there is a thermal resistance from case to ambient. So we'll call that one as R theta case to ambient. So you can split the junction to ambient thermal resistance into two parts. R theta JC, that is the thermal resistance from junction to case, and thermal resistance from case to ambient. The thermal resistance case to ambient will be the major contributor to the entire thermal resistance from J to A. This will be a small part. This will be given in the data sheets of respective components. So R theta JA can be written as R theta JC plus R theta CA. Now this will be around, let's say, 0.5 degrees centigrade per watt. It will vary from component to component, but I am just giving the order of magnitude. And the remaining part will be around 9.5 degrees centigrade per watt for the example that we had just discussed. So this is what that needs to be reduced. So how do we reduce this? We can try to put a heat sink, see that the heat is dissipated, heat flows quickly out into the ambient by putting heat sink, and we could also improve that by Peltier plus heat sink combination. So we will see how we go about doing that. Now imagine this component is sitting on the PCB. We will attach a heat sink to the surface of the component such that it dissipates more quickly. It enables the heat flow that is generated within the component to reach the ambient in a much more quicker manner. So which means we would like to reduce the thermal resistance from the case to the ambient. So we will draw a heat sink. There are many heat sinks in the market. You can look into the thermal resistance that are given in the datasheet catalogs of the various heat sinks by the manufacturers and appropriately choose a thermal resistance. So I draw this heat sink. So this is a heat sink. It has a lot of these fins. Because of the fins, the surface area is increased, and because of the increase in the surface area, the heat can more easily go out through a much more larger surface area. And we have this core which is actually generating the heat, QC. This is the junction. This we will call the boundary between the entire boundary, which I am representing by this dot, where the case of the component comes in contact with the heat sink. At that place I am putting the symbol C, that is the case, represents the case, and this entire heat sink I am calling it as S. And then you have the ambient to which ultimately the heat has to reach to the ambient temperature. That ambient we will call it as A. So if you see that there is a heat QC which needs to be extracted from this junction, passed on to the case, and from case to the sink, and from sink to the ambient. So if you now visualize the thermal equivalent circuit, so I have a constant current source which is having a value QC. Now I will put one thermal resistance here, and I'm calling that one as junction to case, R theta junction to case. Then another thermal resistance, we'll call that one as case to sink. So there is an impedance across the boundary, depends upon how nicely the contact is between the case and the heat sink. So we will say case to sink. And then from sink to ambient, you will have a thermal resistance. So we will call that one as sink to ambient. And then the ambient is the ground temperature, reference temperature. So it's a junction, case, sink, ambient. And we have QC amount of power which is flowing, heat power that is flowing. There is a junction temperature Tj, case temperature Tc, sink temperature Ts, and the ambient temperature Ta. Ambient temperature you have no control because it is dictated by the external ambient. So what is the temperature difference Tj minus Ta? Tj minus Ta is the drops across, temperature drops across each of the thermal resistances. So let us write the relationship Tj minus Ta equals, what is the temperature drop across R theta Jc? It will be R theta Jc into the flow, heat flow Qc. So R theta Jc into Qc plus R theta Cs into QC is the same QC which is flowing through this thermal circuit, plus R theta SA into QC will be the drop, temperature drop across this thermal resistance. So this is our equation. Each is a thermal drop. So this would represent Tj minus Tc. This would represent Tc minus Ts. This would represent Ts minus Ta. So if we use typical values, then let us say R theta Jc of the order of 0.5 degrees centigrade per watt, R theta Cs of the order of 0.1 degrees centigrade per watt, R theta Sa, of course you can buy various different types of heat sinks from the market with different thermal resistance. I will take some typical value 1 degree centigrade per watt, and we know this is QC is 20 watts from the previous example that we discussed, and Ta is 40 degrees centigrade. Of course this can also vary from place to place. For that particular place you could take the ambient, or you should take the ambient if it is within an enclosure. You should take the ambient within the enclosure. Normally if a component is within the enclosure, the worst case ambient within the enclosure is taken as 50 degrees. So now you can compute Tj. So Tj is 40 plus this value, 40 plus this value is 10 degrees, plus this value is 2 degrees, plus this value is 20 degrees. So that comes to 72 degree centigrade. So compare this with the earlier value that we obtained of 240 degrees centigrade. So by putting heat sink, you can actually control the junction temperature to a value which is safe, which is well within the ratings of the particular component. Now if we introduce Peltier junction or a Peltier element in between, then you will see that the R theta SA actually improves much better, and thereby the heat removal is much improved. So how do we introduce the Peltier junction into this. We will have a look at that. We shall now improve the thermal resistance of the sink to ambient S to A or theta SA further by introducing a Peltier cooler in between. So let us introduce this Peltier junction in between. So I will lift the heat sink, and in between I will put this Peltier element. So this Peltier element will have two terminals brought out like this, and to the two terminals you connect a DC-DC converter, and the DC-DC converter is getting power from a PV panel like this, connected in this fashion. There's a capacitance across the input of the DC-DC converter, and power is flowing from the PV source through the DC-DC converter into the Peltier junction, which is providing the electric energy to pump heat from the cold junction, this component which is supposed to be the cold junction, to the heat sink which is the hot junction. So now you could have the DC-DC converter where the duty cycle is controlled, connected to a MPPT controller block, a maximum power point controller block. So this portion would be a maximum power point controlled DC-DC converter interface to a photovoltaic panel. Now when you power up the Peltier junction by passing a current through that, now this component which is generating QC amount of heat, the Peltier junction has to remove QC amount of heat and pass it on to the heat sink. So this block, the component block, will become the cold junction. So the cold junction portion of the Peltier should come on this side, and the hot junction portion of the Peltier should be on the heat sink side. The component will be at temperature which is case temperature Tc. The heat sink will be at temperature which is the heat sink temperature Ts. How do we select this Peltier element? You need to look into the data sheet for these few important parameters. QC, the component is dissipating a power QC, and the Peltier has to move this amount of heat power into the heat sink. So the heat flow will be QC, and QC passing through the Peltier should be less than Qmax from the Peltier data sheet. And another important parameter is IP, the current that is flowing into the Peltier, and that IP should be less than Imax as given in the Peltier data sheet. Ts minus Tc, delta T. Ts minus Tc is the delta T across the Peltier junctions, and this is a design parameter. This is for a particular application. One must decide how much should be the delta T, how much should be the difference in temperature between the heat sink and the case in this particular example. So this comes from the spec of this component, how much case temperature it can withstand, how much junction temperature it can withstand. The designer should appropriately fix the case temperature and the heat sink temperature. So let's say delta T of 15 degrees centigrade. Like that, it should come as a design spec. Now QC is actually the amount of power dissipated in this component. So it could be a MOSFET, it could be a IGBT, it could be an IC, a microcontroller IC, it could be a processing, high power processing compute IC. So the power dissipated here is dependent on the component from which you want to remove heat and keep it cool. So this again is a design spec coming from the other other portions of the system, determined by the other portions of the system. IP actually you can decide from the data sheet after you have chosen the Peltier element. So keeping these factors in mind, delta T is a design spec, QC is a design spec. Let us look at the data sheet and see what information we can gain in trying to decide on the Peltier element. Now in the data sheet, consider this thermographs, Nomo Graph. Now the x-axis is delta T. Now in our application it is Ts minus Tc, heatsink temperature minus case temperature. Now you can define it to some value. We said let us say 15 degrees. 15 degrees means somewhere here. So let us draw a line up at this 15 degrees. So you see that it intersects at 15 degrees, it intersects the Nomo Graph curves, which is a family of curves at different IP currents through the Peltier junction. So here is another point of intersection, here is another possible operating point, so on. So if you see from the requirement, from the design spec of delta T, we have this. Now QC is another design spec, because QC is the amount of heat that the Peltier junction will have to remove from the cold junction, and in this case the cold junction is the component which is dissipating heat. So the QC we said in the previous example of 20 watts. Now let us say 20 watts you want to consider removing from the component, pass it on to the heatsink. Now 20 watt is somewhere here, and almost all the points here are below 20 watts, so I cannot choose that. The only one point is there above 20 watt, which is here. So if I pass 3 amp current, then I will be able to remove greater than 20 watts amount of power and push it onto the heatsink for a temperature difference delta T of 15 degrees centigrade. So this is the operating point that you need to consider, which is greater than 20 watts QC, and you should pass around 3 amps of power, 3 amps of current through the Peltier junction, so that it has enough energy to lift this heat QC amount of heat flow and pass it on to the heatsink. So in this way you can decide that the Peltier should at least have a power rating of greater than 20, around 24 or 28 watt Peltier element can be chosen, and appropriately from the Nomo Graph, seeing Nomo Graph, seeing the point of intersection with the QC and delta T, you can decide how much amount of IP current should be fed into the Peltier junction. It becomes very important now that the heatsink, the heat that is put into the heatsink, should be removed at the rate that the Peltier junction is allowing the heat flow from the junction of the component to the sink. So this QC, rate of heat flow, should be maintained from the sink to the ambient. Otherwise the sink temperature will rise. Once the sink temperature rises, you will see that the TC temperature will also rise, that is the case temperature will rise, because your delta T is fixed by the Nomo Graph and the amount of current that you are pumping into the Peltier element, and as a consequence then the junction temperature TJ will rise. So therefore it is important that it is not only enough if you make the Peltier junction to remove the heat from the cold side, put it into the hot side, but you should also design your system in such a way that this heat sink is capable of removing the heat out from the sink into the ambient at that same rate. Only then the whole system together will work properly as a cooler. So you will see that there are many products where just the plain heatsink is not sufficient. If sufficient cooling is needed, the heatsink has to be made very big, and that may be cumbersome or it may not fit into the enclosure. So the heatsink is made small. They will add additionally a blower, a fan, something like this. So this fan has two terminals and blades, and this fan will be driven from the output of the DC-DC converter. One more set of terminals is available from the DC-DC converter. So this DC-DC converter should be a multi-output DC-DC converter, and that will get connected to the fan and control the fan. So the fan will enable forced cooling. It will enable flow of air through the fins of the heatsink and remove the heat at a much more rapid pace. The fan together with the heatsink will have a thermal resistance R theta sink to ambient, which is much lower than just only the plain heatsink. Therefore, for a given sized heatsink, forced air cooling will lead to much faster heat flow through the heatsink. So this fan coupled with the DC-DC converter, MPPT, all these electronics driving the Peltier is generally referred to as a thermoelectric controller. So this would be a total Peltier cooling system that you can find in many products in the market.